Hello everyone, this is Greg from ChemCore. If you haven't noticed, a little bit of the explainer videos is different. I now have a little green screen behind me and I'm going to be showing my face on the explainers as well. I hope that this is going to make the videos a little bit more interactive. There's going to be a lot more moving parts on the screen. I feel like before it was kind of stable. I would stay in one spot on the screen, and I feel like that would get maybe a little bit boring. In addition, I'm able to kind of point and kind of, show my face and use my hands. And so I feel like this is going to make things a little easier and just a little more interesting. In this video, we're going to be going through the acid-base strengths explainer video. If you haven't had a chance to look at the worksheet for this, it is linked in the description below. The answer key is also available in the description below. We're just going to be going through it as I would solve the questions. And if if you're not familiar with this, or you feel like you're a little behind, I have a topic video, really quick, maybe 5 minutes, that is really going through these topics. And so before really going through this worksheet, I suggest to go watch that. That is also in the description below. Before we start, let's remind ourselves on some of the important topics or important points about determining which species could be the stronger acid. So in the past couple of videos, we talked about Bronsted-Lowry, Lewis acids and bases, and we just kind of broadly defined what an acid and base is. And we also mentioned in this video, in the topic video, that unlike general chemistry, where you kind of just learn the strong acids and the strong bases, organic chemistry is not so black and white, right? You have a lot of these organic species, which all of them aren't strong acids. And so how do you know whether one is an acid, one is a base? And so in most cases, acidity and basicity is on a spectrum. Water, for instance, can act as an acid in one environment, while in another environment, it can act as the base. And so it really depends on what else is in, the mixture or the situation. And so there's a couple principles or rules that we can follow as a checklist, kind of going down the list to determine which species is going to be stronger, which species is going to be weaker. And so in the video, if you're not familiar with this, I go into a lot more depth, but just, quickly summarizing, the rule is called ARIO. I like to call it ARIO. And we're going to be adding kind of another letter to this. A refers to atom. And so if you were to pull up your periodic table, acidity increases to the right and down. So kind of going toward electronegativity, but kind of going down. So electronegativity increases right and up. Acidity increases right and down. So kind of toward fluorine and then down toward iodine. And so if you're comparing a proton, according to the Bronsted-Lowry definition, because that's the easiest for organic chemistry, and it's connected, the proton, the acidic proton, is connected to different atoms, well, that's easy, right? So which atom, according to the periodic table, is going to be more acidic? And chemically, the reason for this is, well, some atoms are bigger, and so they can kind of, get an extra lone pair if they do give away the proton. Some atoms are just not willing to give away a proton at all, like carbon, something that we're going to focus on a lot later in the future. It's a really important point. Let's say the atoms are the same. What do you do next? Well, the next point that you can kind of compare is resonance. Now, if, let's say, both the protons are connected to an oxygen, while one of them is an alcohol, the other one might be a carboxylic acid. They're both connected to oxygens, but the carboxylic acid inherently has more resonance. And so because it has more resonance, it'll be more acidic. But let's say both the compounds have the exact same resonance. What do we do then? Then we can compare something called the inductive effect, right? Or we can just shorten it to induction. Now, the inductive effect refers to other electronegative species existing close to the proximity of the acidic proton, like fluorine, chlorine, bromine, iodine, right? Oxygens, other kind of atoms that have a strong electronegativity to them. The reason for this is because they're pulling some of those electrons away, and so if that atom was to give away the proton and get an extra lone pair, it's not too unhappy about giving away the lone pair. It's kind of, being pulled away and it's being shared by these other electronegative atoms. But let's say the inductive effect is the same. At this point, and this usually applies to more carbons, we go toward the orbitals. So the rule is as our sp decreases, our acidity increases. What do I mean by that? Well, most commonly you'll see sp3, sp2, and sp, right, or sp1. And so as that number decreases from sp3 to sp2 to sp, or sp1, the acidity increases. And the reason for that is because we have more bonds, right? More pi bonds, more electrons being shared. And so if we were to get an extra lone pair from that loss of a proton, we'll be able to kind of move that around a little easier, and it's just able to handle that charge a little better. Now, what kind of throws this whole thing in the drain is charge. And so sometimes teachers will kind of introduce this as ARIO. I find this difficult. I used to do that with some of my students. It gets confusing if you consider this kind of like first in the mix. I like to consider it kind of like separate. I want you guys to follow ARIO and then consider charge separately. Now, charge is going to be something that completely throws everything off. And most commonly, what you'll see is a positive charge on the acidic kind of atom, the atom bearing the acidic proton. What that causes is way higher acidity than predicted, right? Let's say a nitrogen. According to the atom rule, you would predict that nitrogen is going to be less acidic than oxygen. If nitrogen was positively charged like ammonium, those rules go out the drain. The nitrogen is now much more powerful than in regular oxygen. Kind of, there's kind of some exceptions. It's not stronger than a carboxylic acid. Chemistry is chemistry. There's nuance and everything. But because of that, the charge kind of throws everything off. The reason for that is because a positive charge means that you have an extra bond. So you're just literally trying to give away an extra bond, right? You want to be neutral. And so why not give away that proton? It all works out, right? And so that charge really throws everything off. You won't see negative charges as much because it's assuming you already have a lone pair. And so usually negative charges are not going to be acids at all. They're going to be bases, right? Because they already have an extra lone pair. And so some of the principal rules is something called pKa and pH. Now, pH is something that we don't really talk about in Orgo much because it's very basic. It doesn't really mean much in our case. What we really want to talk about is pKa. And so I mentioned pKa. pKa is an actual strength of dissociation of the acid. So how well does the atom or compound lose that proton, right? And so this is actually a direct measurement of how strong the acid might be. And pKb is an opposite measurement of how strong the base might be in kind of gaining that proton. Now, what's also important to realize is that as the acid becomes stronger, the basicity of its conjugate base becomes weaker. For instance, a strong acid, like sulfuric acid, its whole point is to give away the protons that it gained, right? It's strong. It wants to give them away. So once it does, why would it want it back, right? And so a strong acid, for instance, will be a really, really weak base because it did its job. It's not going to go backward, right? And so this is kind of a really great way to remember, if you're asked to compare basicity, a shortcut I like to do is let's write the acid for that and then just compare acidity. There's no new rules that you have to learn. You don't have to think about it backwards or anything. It gets confusing, right? And so if you're asked for the strongest base, let's look for the weakest acid. If you're asked for the weakest base, let's look for the strongest acid, so on and so forth. And so let's really start. The first question is kind of simple. They're asking us which of the following organic compounds is the strongest acid. Now, you don't really have to compare anything if they give you the pKa's. If they give us the pKa's, all we're looking for, and this should be familiar from your general chemistry courses, is the compound with the lowest pKa value. And so, I'm not even looking at what the compound is. pKa 0 is much smaller as a value than the other pKa's, and so that's going to be our strongest acid. Now, the other question is kind of in the same kind of area of using pKa to our advantage, but they're asking us for the strongest conjugate base. And so again, I don't like to learn extra rules, right? I have one rule, I'm going to use it. A strong conjugate base means that we have a weak acid. And so because we're looking for a weak acid, we're looking for the compound that has the highest pKa value, which just turns out to be A, right? 52 is the highest of the list. Now, question 3 is kind of a nuanced question. Not all courses will give you the chart that I gave. It's available on my website as well as in the description of the topic video. There's a chart with kind of pKa values of common functional groups and compounds that you might see. And so not all courses will give that. My course did. People I know, they didn't get this chart. And so if you don't get a chart, you're not required to memorize pKa values. But if you do, this is kind of a good chance to use it. You want to go to your chart and try to figure out, okay, which compound looks, to be similar with a pKa of 25. And what you'll realize is that if you go to your chart, sp hybridized carbons have a pKa of around 25. And so let's look for the compound that has an acidic proton on an sp hybridized carbon. And that turns out to be answer choice C, because this hydrogen is on an sp3 hybridized carbon. And you might be asking, well, hold on, what about this? Well, this hydrogen is attached to an oxygen, right? That's not sp hybridized. This one looks a lot like it's right next to sp hybridized carbon, but it's actually on an sp3 hybridized carbon. This is sp2 hybridized, well, this is a nitrogen. In question 4, they're asking us which hydrogen atoms from which positions are most likely to be abstracted when the following substance is treated with NaH. This might seem like a confusing question. It's really not. All they're asking you is which atom is most likely going to be able to give away a proton when treated with a base, right? NaH. And so let's look for the atom, or which position is the strongest acid, right? Is strong acidically. And so if you remember your orbital rules, all of these hydrogens that aren't drawn because it's a bond line structure are connected to carbons. So our atom is the same, our resonance is the same, they're all carbons. Our inductive effect is the same. We don't have any other electronegative groups. It boils down to orbital. And what did I say? As our sp kind of value comes down, acidity goes up. And so the position that I have, most sp hybridized are 1 and 2, right? Now, you might be tempted to circle C. The problem is that position 2 doesn't have any protons. If you looked at it, it already has 4 bonds. Where are the protons? The only carbon that is sp hybridized and has hydrogens is position 1. And so the answer choice, the correct answer is A. Now, number 5 is kind of a very common type of question that you'll get when it comes to comparing acid-base strength. They will give you a complicated molecule, they'll label some of the atoms, and ask you to rank hydrogen atoms from, highest to lowest acidity. And so this is where the rules of ARIO come really in handy. I don't like looking at molecules like this, so I'm going to teach you a strategy to kind of go through these problems. If the structure isn't drawn, you kind of want to draw it out. Fortunately for us in this problem, the structure is drawn out. So let's kind of go break it down, and let's break down each proton and what it's connected to. That's really going to help us compare what we have. And so HA, hydrogen A, is connected to a positively charged nitrogen, right? HB is connected to a carbon, and carbon isn't enough. Let's mention that it is also sp2 hybridized, right? That's important. It's double bonded. HC is connected to a positively charged oxygen, and HD is connected to just a regular oxygen. And so some additional information that we might need, like resonance or inductive effect, we'll go back to the structure if we need it. But just doing this will solve a lot of problems just by knowing your atom rules or charge rules. It really is just gonna help you out a lot. It's gonna simplify the questions. And so the first thing that I want you to understand is that, well, ARIO, we start with A, right? We want to look at the atom first. According to the periodic table, oxygens compared to nitrogens and carbons are going to be the most acidic, are going to be able to kind of give away the proton the best. But let's compare. Well, there's a big difference between these oxygens. There's a positively charged oxygen and a neutral oxygen. Which one is going to be stronger? Probably the positively charged oxygen, right? Because that charge rule. Charge kind of throws everything out of the garbage. And so we're probably going to say that this is number 1, right? And because of this oxygen, well, now we're comparing this oxygen and the nitrogen. Now, I mentioned these exceptions in the topic video. If you're not familiar with that, go check it out. One of the exceptions is that positively charged nitrogen may be stronger than oxygens, even though that goes against your ARIO rules. The problem is, not always. Positively charged nitrogens are stronger than alcohols, but not carboxylic acids. And so I say that because that's the most common example that you'll get. What I really mean is that positively charged nitrogens are stronger than oxygens that have no resonance. Alcohols don't have resonance. Carboxylic acids do. And so because of that, I like to say, because it solves most of the questions, positively charged nitrogen is going to be stronger than an alcohol, but weaker than a carboxylic acid. And so once you see positively charged nitrogen, I want you to pause and take a step back. Look at the other oxygens and just slow it down for a bit. This oxygen is a part of a carboxylic acid, right? Therefore, it is still going to be stronger than your positively charged nitrogen. And so we're going to say that this is number 2 priority. Obviously, comparing nitrogen, especially because it's positively charged to carbon, the positively charged nitrogen is going to be number 3, and the carbon is going to be number 4. And so if we had to go from highest to lowest in acidity, we're going HC, HD, HA, and HB. So our answer is C. In question 6, we're looking for the strongest acid. And so again, let's break it down, even though it's not drawn out for you. They're more or less simple structures. And so we can kind of just break down each of the answer choices and write down for us what kind of atom or what characteristics does the carbon bearing the acidic proton have, or atom bearing the acidic proton have in each answer choice. And so in answer choice A, we have a hydrogen connected to just an oxygen, right? And we could just say that it's an alcohol, right? That might come in handy. In B, we can say that this is an oxygen that is a carboxylic acid. And so I like to mention functional groups, especially when it comes down to oxygens, because you'll often have to compare oxygens that are carboxylic acids or alcohols. And if you just remember in the back of your head that carboxylic acids, because of that double bond, have an inherent resonance to them, you will realize that, okay, carboxylic acids in most cases are going to be stronger than alcohols. And so I like to write down the functional group when it comes down to that. C, we have it's connected to a carbon that is sp hybridized. That's very important to mention. In D, it's connected to a carbon that is sp2 hybridized. And in E, it's connected to a carbon that is sp3 hybridized. And so just breaking this down is really going to help us. Remember your ARIO rules, atom, oxygens are going to be much more acidic than carbons. So we can kind of just, cross C, D, and E out. It's not going to be a stronger acid than A and B. And so now we're comparing, okay, oxygen and oxygen, we have to move down to resonance. And this is why writing the functional groups comes really in handy, because carboxylic acids have resonance, alcohols don't. So because of that, we can say that more resonance, higher acidity, answer choice B, or the carboxylic acid, is going to be the strongest acid. In question 7, which of the following correctly lists the compounds in order of decreasing acidity? And so we want acidity stronger on the left, weaker on the right. Now, you may be tempted. I think one strategy is just to go through each answer choice one by one. What you might realize is that every answer choice kind of has the same compounds in different order. And so because it has the same compounds, let's just break down every compound and order them in decreasing acidity, and then we'll just match it to the correct answer, right? And so one of the first compounds that we have is H2O, right? And we can say that this is connected to an oxygen with basically no resonance, right? So we're just going to say oxygen. The next compound that, we'll see is, triple bonded carbon. And so what we can say is it's connected to a carbon that is sp hybridized. The next is NH3. And so that is nitrogen that's, just regular. There's no positive charge, nothing remarkable about it. And then CH3, that is just a carbon that is sp3 hybridized. And so if we had to consider in decreasing acidity, this is where one of the other exceptions come up. Another exception to the rule that there's not a lot of these exceptions. If you remember them, you'll be good. A sp hybridized carbon is stronger than a neutral nitrogen. According to your ARIO rules, you might predict that nitrogens are always going to be stronger than carbons. That's not always the case. And sp and only sp hybridized carbons are stronger than neutral nitrogen. And so because of that, we're going to rank this, oxygen, right, number 1. The exception will rank the sp hybridized carbon as 2. And nitrogen, we're going to rank it as 3. And the sp3 hybridized carbon, the weakest types of compounds you'll ever find, is going to be 4. And so actually, the answer choice matches up our ordering perfectly. In question 8, we're asked to rank the boldface hydrogens from the following compounds from most acidic to least acidic. So let's use our strategy under each structure and kind of write down what the acidic proton is connected to, and then we'll just kind of analyze it. And so in structure 1, it's connected to an oxygen that is a carboxylic acid, right? So we have a good amount of resonance. In structure 2, we're connected to a nitrogen that is positively charged. That's important to mention. In structure 3, we're connected to a carbon that's, just sp3 hybridized, probably going to be the weakest. In structure 4, we're connected to an oxygen that is positively charged. That's really important to mention. And then in structure 5, we're connected to a carbon that is sp2 hybridized. And so now with our analysis, let's look for the most acidic structure. What I'll probably want to look at first is the oxygens and the positively charged nitrogen. That's an important exception to remember. Keep in the back of your head. What I also remember glaring at me is that in structure 4, we have oxygen with a positive charge. Cario, right? Charge throws everything out of the water. A positively charged oxygen is going to be way stronger than anything we can find, right? Even the carboxylic acid, even though it has resonance. And so because of that, we're probably going to say that this is our strongest structure. And then we're left to compare 1. You might be tempted to kind of put the carboxylic acid right away, but remember your exception, nitrogen positively charged. Okay, remember nitrogen positively charged is going to be stronger than alcohols, weaker than carboxylic acids. And so we'll, keep our original assumption. Yes, structure 1 is going to be second on our list. And then structure 2, and nitrogen is going to be third on our list. And then we have to compare sp3 to sp2 hybridized carbons. And we can understand that as sp value decreases, acidity increases. And so we can say that structure 5 is going to be our fourth strongest, and then structure 3 is going to be our weakest. You can kind of usually just, if you see an sp3 hybridized carbon, it's usually going to be the weakest acid in the list. And so the answer choice that matches that is D. In question 9, similar question. Let's rank them from most acidic to least acidic. We have a hydrogen attached to a carbon that is sp hybridized. In structure 2, we have hydrogen attached to an oxygen that is positively charged. Question 3, we have a hydrogen attached to carbon that is sp2 hybridized. Structure 4, we have a hydrogen connected to oxygen that is a carboxylic acid. And in structure 5, we have hydrogen connected to nitrogen that is, nothing special. And so let's organize them from most to least acidic. The first thing that I want to look at is atom, so oxygens. The positively charged oxygen is going to be much stronger than anything else. And then we're left to compare the carboxylic acid. Well, the nitrogen is nothing, doesn't have a charge in it, and so we can say confidently that the carboxylic acid is going to be second strongest. Nitrogen is obviously going to be third strongest. And then we're comparing sp to sp2. Sp hybridized carbons are stronger than sp2 hybridized carbons, and so structure 3 is our least acidic. And so the answer choice that best matches that up is answer choice B. In question 10, again, we're looking for the structures to order in most to least acidic. And so in structure 1, the hydrogen is connected to carbon that is sp3 hybridized. Question 2, it's connected to a carbon that is sp2 hybridized. Structure 3, we're connected to a nitrogen that is positively charged. In structure 4, we're connected to a carbon that is sp hybridized. And in structure 5, we're connected to an oxygen that's just an alcohol. And so you might be tempted, according to your ARIO rules, oxygen is much stronger than nitrogen. There's an exception. Positively charged nitrogens are stronger than alcohols, weaker than carboxylic acids. Therefore, structure 3 is actually our strongest acid. Structure 5, or alcohol, is our second strongest, and then we're comparing sp to sp2 to sp3. Sp is obviously going to be strongest, and sp3 is going to be our weakest, and so we can organize them as 3, then 4, and then 5. And so the answer choice that best matches that up is answer choice A. Again, question 11, we're looking to organize them from most to least acidic. And so in structure 1, we're connected to a carbon that is just sp3 hybridized. Structure 2, we're connected to a nitrogen that is positively charged. In structure 3, we're connected to a carbon that is sp2 hybridized. Structure 4, we're connected to a carbon that is sp hybridized. And structure 5, we're connected to an oxygen that is a carboxylic acid. And so you might be tempted, let's put oxygen in front first. Let's remember our exception. I'm going to keep repeating this over and over and over again. You need to remember this. Positively charged nitrogens, stronger than alcohols, weaker than carboxylic acids. And so yes, the carboxylic acid is going to be our strongest acid. Nitrogen is going to be our our second strongest acid. And then sp is going to be 3, sp2 is going to be 4, and then sp3 hybridized carbons are going to be our weakest. And so the answer choice that best matches that up is C. Question 12, let's organize from most to least acidic. In structure 1, we have a hydrogen connected to nitrogen that is positively charged. In structure 2, we have a hydrogen connected to a carbon that is sp hybridized. Structure 3, it's connected to an oxygen that is a carboxylic acid. Structure 4, we have a hydrogen connected to a carbon that is sp2 hybridized. And structure 4, we have hydrogen connected to an oxygen that is positively charged. And so let's compare. We have nitrogen positively charged, an oxygen that's a carboxylic acid, and an oxygen that's positively charged. Positive charged oxygen knocks everything out of the park, so that's going to be our most acidic. And then remember our exception, nitrogen stronger than alcohols, weaker than carboxylic acids. And so the carboxylic acid is going to be our second strongest acid. Nitrogen is going to be our third strongest acid. The sp3 hybridized carbon is next. And then the weakest is going to be the sp2 hybridized carbon. And so the answer choice that best matches this up is answer choice E. 13, again, we're organizing from most to least acidic. And so answer choice 1, we're connected to an oxygen that is a carboxylic acid. Structure 2, we're connected to a carbon that is sp2 hybridized. Structure 3, we're connected to an oxygen that is positively charged. Structure 4, we're connected to a carbon that is sp3 hybridized. And structure 5, we're connected to an oxygen. Now, this oxygen is not a carboxylic acid. It does, though, have a lot of resonance. And so we kind of want to consider that, right? It has a lot of resonance, and it also has kind of a bunch of these carbons around. So that might be an issue, right, in the future. And so I see a positively charged oxygen. I know right away this is going to knock everything out of the park. This is going to be our strongest acid. And now we're left to compare these two oxygens, structure 1 and structure 5, that have a lot of resonance. They're on a ring. And so what we're left with is, okay, they both have resonance. What's next? Inductive effect. And so we're looking for groups that are close to this oxygen that are strong negativity. And so you're looking at the CF3 and these kind of methyl groups. Now, one thing that you have to remember is that methyls, additional carbons, are kind of the opposite of inductive effect. They reduce the acidity. They are not electron withdrawing. They don't have strong electronegativity. They're fairly weak compared to other atoms. And so structure 1, these fluorines, are going to have an effect inductive, right? They're going to pull some of these electrons away. And so this causes our first structure to become the second strongest acid. Structure 5 is going to be the third strongest acid. And then we're left with sp2 and sp3. sp3 hybridized carbons are your weakest acids. And so structure 2 is our fourth strongest acid. Therefore, the answer choice that best matches this up is answer choice D. Question 14, let's organize from most to least acidic. In structure 1, we have a hydrogen connected to a carbon that is sp2 hybridized. In structure 2, we have a hydrogen attached to an oxygen that is a carboxylic acid. Structure 3, we have a hydrogen connected to a carbon that is sp hybridized. Structure 4, we have a hydrogen connected to a carbon that is sp3 hybridized. And structure 5, we have a hydrogen connected to a nitrogen that is positively charged. And so let's compare all of these. We're probably going to look toward the oxygen that's a carboxylic acid and the nitrogen that's positive. Remember our exception, positively charged nitrogens are stronger than alcohols and weaker than carboxylic acids. And so the carboxylic acid is our strongest acid, followed by the positively charged nitrogen, and then our sp3 hybridized carbon, our sp2 hybridized carbon, and our sp3 hybridized carbon. And so the answer choice that best matches that up is B. Again, question 15, let's rank from most to least acidic. In structure 1, we're connected to a carbon that has a lot of resonance, interestingly enough, and it is sp2 hybridized. In structure 2, we have a hydrogen connected to an oxygen that is positively charged. In structure 3, we're connected to an oxygen that is a carboxylic acid. In structure 4, we're connected to a carbon that is sp hybridized. And in structure 5, we're connected to a nitrogen that is positively charged. And so positively charged oxygen is going to knock everything away. This is our strongest acid. And then remember, nitrogen, positively charged nitrogens, are stronger than alcohols but weaker than carboxylic acids. So that makes number 3 our second strongest acid. And then structure 5 is next, followed by the sp hybridized carbon, and then the sp2 hybridized carbon. And so the answer choice that best matches that up is B. In question 16, we're kind of given small compounds and asked to find which one is the most acidic. And so let's kind of write down what the acidic hydrogens are connected to. And so in answer choice A, we're connected to an oxygen that's just an alcohol. In answer choice B, we're connected to a carbon, that has bromine, so some inductive effect, but, it's still not much. And in C, we're still connected to a carbon. There's a chlorine, so a little bit more inductive effect, but still probably not going to do much. D, we're connected to a sulfur. And then E, we're connected to a nitrogen. Now, what I want you to notice is there are no charges, right? And so we can kind of just go down ARIO and have no doubts. And so if you go down ARIO and you compare, okay, which atom is most acidic, you'll find sulfur, right? It goes from nitrogen to oxygen to sulfur that's under. And so because acidity increases to the right and down, sulfur is going to be our most acidic atom out of the answer choices. In question 17, they're asking us which of these compounds is least acidic. Now, what you'll notice is that all of these acidic protons are all connected to oxygens that are all carboxylic acids. And so because they're all connected to oxygens, ARIO, A, we can knock that out. R, resonance is completely the same. We're going down to induction, right? Inductive effect. And so we're looking at other atoms around the acidic oxygen that have the most electronegativity. And what I see is fluorine, right? Fluorine is the most electronegative atom on the periodic table. And so the fluorine next to the acidic oxygen is going to make that oxygen a lot more acidic than any of the other structures. And so what is the least acidic? Well, the structure with the least inductive effect, right? The less amount of electronegative groups. And so that's going to be structure 1, right? The one with literally no inductive effect. And so because of that, our answer is A. In question 18, we're looking for which of the compounds is most acidic. Again, all of these acidic protons are connected to an oxygen that's a carboxylic acid. And so it goes down to induction. Which one of these structures has the most inductive effects, so the most electronegative groups as close as possible? Now, what I like to do when having these type of questions is we see a bunch of bromines. Let's figure out which one has the most bromines, right? The more electronegative groups, the more induction. And so structures 1 and structures 5 only have 1 bromine, meaning that they're not going to be the most acidic for sure. The rest have 2 bromines. And so let's try to find the structure that has the most bromines as close as possible. And that ends up being structure 3, right? We have both of the bromines as close as possible to the oxygen, meaning that they have the most effect inductively, right? And so our most acidic structure is going to be structure 3. In question 19, we're asked which of the protons is least acidic. Let's just, analyze it as we usually do. Proton A1 is connected to a carbon that is sp3 hybridized. Carbon 2 is connected to a sulfur. Carbon 3 is connected to a nitrogen. Carbon 4 is connected to an oxygen that's a carboxylic acid. And proton 5 is connected to a regular oxygen that's just an alcohol. And so if we're looking for our least acidic, as soon as you see least acidic, I want your eyes to go to the one to sp3 hybridized carbons, because that is going to be the least acidic atoms that you'll ever find, right? At least in this course. And so because of that, proton A ends up your least acidic proton. And now, because of this, it kind of makes sense. Oh, so that's why carbocations and carbanions really don't like to be formed, like we talked about in the Lewis acid video. It's really hard for a carbon to lose a proton. And so it's really hard to become a carbocation or carbanion. And so because of that, even when we do form them, they're very, very short-lived, like basically fraction of a second, right? Incomprehensible amount of short time. Question 20, we have a similar question. Let's figure out which of these protons is the most acidic. So proton 1 is connected to an oxygen that is an alcohol. Proton 2 is connected to just a regular sp3 hybridized carbon. Proton 3 is connected to a nitrogen that is positive. Proton 4 is connected to another carbon that is sp3 hybridized. And proton 5 is connected to just a nitrogen. And so you'd be tempted to answer proton 1. It's connected to an oxygen, ARIO, right? But exceptions, positively charged nitrogens are stronger than alcohols, weaker than carboxylic acids. And so proton 3 is actually the most acidic, meaning that our answer is C. In 21, now this is what I mentioned earlier in the video. What if they ask us about basicity? And so what I like to do is, even though they might not have a proton, let's imagine the indicated atoms as if they have a proton. And so if we can organize them from strongest to weakest acid, we can kind of do the opposite. If we're looking for the most basic, we're looking for the least acidic. And so structure 1, we have it connected to an oxygen that's a carboxylic acid. Site 2, if it did have a proton, this would be a oxygen that's also a carboxylic acid. Proton 3 is connected to an oxygen that is an alcohol. Site 4 is connected to a nitrogen, right? And site 5 is connected to a nitrogen that's actually an amide. So that's not something that we've seen earlier in this video, but that's also a lot of resonance, right? And so if you're looking for the most basic, let's look for the site that's the least acidic. That makes nitrogen, right? Nitrogen, just regularly charged nitrogen, neutral, is going to be weaker than pretty much everything else on this list. There's no resonance. There's nothing really going on. And so because of that, our answer is D. This is going to be the most acidic, this is going to be the most basic atom. Question 22, we're looking for the indicator proton that's the most acidic. Let's break it down like we usually do. Proton 1 is connected to a carbon that is sp3 hybridized. Proton 2 is connected to a nitrogen. Proton 3 is connected to a nitrogen that is positively charged and it's an amide. Oh, that's, pretty big. Proton 4 is connected to just a positively charged nitrogen. And proton 4 is connected to an oxygen that's just an alcohol. And so because of that, I'm kind of looking right at the nitrogens that are positively charged, because both of them are going to be stronger than the alcohol. Except proton 3, not only is it a positively charged nitrogen, it's also an amide, which means it has a lot of resonance. And so because of that, proton 3, the one connected to an amide, is going to be the most acidic. This question concludes the worksheet on acid-base strength. If you're not super familiar with these concepts and you want to review, there's always a topic video linked in the description below to review. They're very quick. They go through everything at a pretty fast pace. It's not going to take up a lot of your time. And if you want to ever redo these worksheets or just look at the answer key, they're all available in the description below. And I'll see you guys in the next video.